text generation or word prediction isn't a new domain in the field of artificial intelligence. Do you remember life before 2017? How do they predict word, next word, or generate text? We have had neural network models called RNN. Anyone knows what's RNN? Recurrent neural network. Okay. Anyone have done deep learning over here? Okay. Anyone else deep learning? Okay. You will learn it in your deep learning class. So we have had RNN models, recurrent neural network, and also the advanced kind of models called long short-term memory, LSTM. These kinds of models predicting your next word or generating text. But the problem with those models was memory problem, and it has to process words in sequences. And there is also context, it forgets context. So all these drawbacks made the research not to be able to progress rapidly in this field. Until one fine day in 2017, a group of 8 researchers in Google Brain published a paper. Anyone knows what's the title of the paper? Okay. The paper is called Attention is All You Need. Attention is all you need. And when they published that paper, even those researchers didn't know that that paper is going to cause a kind of a revolution in the field of AI only 5 years down the road. So 2017, the paper was published, and then what happened in 2022? Yeah, you started to see ChatGPT coming out. So the publishing of that paper was the ignition point of all the transformer architecture and also the large language models that we are ubiquitously using today. So good morning, my name is Jeffry. I previously worked as a data scientist with Petronas Digital. I'm currently building a company, a software company for environment, social, and governance with my partner. Just to manage expectation today, I'm not a research scientist in large language models or transformers. Okay? I'm just a curious cat who wanted to understand what happens under the hood in these large language models. So when this opportunity for this workshop came about, I took it, and then I just dig deep a bit so that I can do this sharing with you guys. Anyone who doesn't use LLM over here, ChatGPT, Gemini, Claude, just rain check. Okay. So before we go into this, why do you need to learn the basics? Why do you need, look at the second question. Why do you need to learn the basics or the fundamentals? How many of you are computer science students? So all of you are. Okay. What are the rest studying? You guys? Computer science. Okay. So anyone not from computer science? Okay. So that would mean that let's say once you are done with studying and you go into this generative AI field, okay, and your company wants you to fine-tune a pre-trained model. So before you can fine-tune a pre-trained model, you need to understand how it was trained, how it works under the hood for you to make modification to it, right? And the second reason is, I think you might be also seeing in your social media everything about agents, multi-agents, all kinds of agents. Okay, if somebody gave me $1 when someone mentioned agent, I would be a billionaire this week. That's how much I have heard about agents in the past 1 month. So, in order for you to use LLM models to build your agents, you also need to know what's happening under the hood, how the model works. And third reason is, let's say you want to build your own frontier models like OpenAI, Gemini. Malaysia also might want to build its own frontier models for AI sovereignty in the future. So for that, you also need to understand what's happening at the first level itself, so that you can build 2 optimization techniques and build a better model in the future. So those are my 3 motivations why you should learn what's happening in an LLM model. And when I dig deep into it, these are the first 3 questions are some of the questions that I found answer to. Let's just check those questions. Have you realized when you keep on using a chat in ChatGPT or Gemini, when you are using it for a long time, and then it tends to forget what the instructions that you gave a long time ago. Have you realized that? Or when you use agents, you might have told it, be respectful in your tone, but then somehow you see that on the third day or fourth day, it becomes in a different tone. Have you realized that? Okay, so those are the kinds of questions you can get answered if you try to go a little bit deeper into how those LLM works. And the second one is, when you put a query in ChatGPT, it doesn't display all the words in one go. It streams word by word. Have you ever asked why it streams word by word and not everything in one go? Or anyone knows why it streams word by word? Feel free to just shout out, guys, your answer if you know. Sorry?
The chat is predicting the token.
Yes, it's predicting the tokens, but it's predicting one at a time. Okay, so it predicts one word and then it sends back into the architecture and predicts the other word. So that's why it's coming out on your screen one word by one word. Okay, and the third one, the magical question: why is the output non-deterministic? Same query, I put in two different chats, I will get totally two different answers. Why am I not able to get a deterministic output? So if I use a calculator, I put 2 plus 2, every time I'm going to get a 4. There is no way I can get a 5. But why in chatbots, I get totally different answers every time? Anyone? Yes, it's in the architecture, okay? We will see when we go into the architecture, we will see what happens at the final stage that causes the next word to be different every single time that you use, okay? Let's move on. Okay, all of us use ChatGPT, right? I'm sure most of you would know, but I just want to do a check. Who knows the full form of GPT? Yes, you guys would like to try full form of GPT? Or maybe, I mean, it's, yeah, go on. Generative pre-trained transformers. Feel free to just Google up, okay? I mean, nowadays everything is in your fingertip, okay? Generative pre-trained transformer. So the word generative is self-explanatory. So it's generating, it used to generate text. Now it can generate image, videos, and voices. The pre-trained, we will look why it's named pre-trained later when we go through, okay? And transformer is the name of the architecture using which these models have been built. Okay, so when I say architecture, when you build a building, there are some architecture that you will be following. Like there should be washrooms over here, there should be staircase. So these are architecture, and using this architecture concepts, the buildings are being built, right? So transformer is the architecture based on which these models have been trained and deployed into these applications. Okay. Now, before we go into the working mechanism of these models or the architecture, I would just like to do a simple review of two mathematical concepts. Okay, one is dot product. All of you have done linear algebra over here. Okay, so I'm sure you would have done dot product computation. So when you do a dot product between two vectors, you multiply each of the element and then you sum across it. Okay. All the screenshots with that black background, I took it from 3 blue and 1 brown YouTube video. I'm not sure why is the credit not coming up over there, but because I tried to do it by my hand, it looks horrible. So I just took a screenshot of it. Okay. So basically, when you take a dot product, you multiply each of the element and you sum them up. That's mathematically. But anyone can tell me, what does the dot product mean geometrically? What meaning do you assign to a dot product geometrically? What I mean by that is, what does it mean to you when you see a dot product? What meaning do you assign to it? So right now we are taking a dot product between that vector and the vector in the yellow. So when you see a dot product of -0.11, how do you interpret that number? Anyone? Okay, let me help out with that. When two vectors are close to each other, then your dot product is going to be positive. When two vectors are further away from each other, and your dot product is going to be negative. What if your dot product is 0? What does it mean if your dot product is 0? Anyone like to take a guess? It means your vectors are perpendicular to each other. If this vector is perpendicular to the other vector, then your dot product is going to be 0. Okay, so that's how you interpret dot products geometry. You will see why this is important in a while when I go to the architecture. But there's only one more mathematical concept that I would like to review before we go into the architecture. Okay. Since you guys have not done deep learning yet, so I'm sure no one has come across softmax. Anyone have come across softmax before this? Okay, so softmax is called an activation function. I don't want to go into the details of it, but I will just give you a simple explanation of what this softmax is doing so that you can understand the architecture better. So on your left hand side, you see an arbitrary vector, right? Those numbers are very random from 0 to positive, so from -2 to positive 8. What if I want to change these numbers to a number between 0 and 1? And when I sum them up, they total up to 1, like this. It becomes like a probability distribution. Okay, so I want to transform from left arbitrary vector to a vector of 0 to 1, and when I sum up, it becomes total up to 1, so that I can have like a weightage over here. Okay, so that's why we do softmax, to convert arbitrary vector into a probability distribution between 0 to 100%. Okay, so this is the operation that we do to do this kind of transformation. It's called softmax. Again, we will see why is it important when we go into the architecture. So that's it. No more mathematical review. I'm not sure why is the lag between the slides. It's probably it's pointer. Okay. Let's go into this. The fundamental concept of understanding these LLMs or transformer is you need to understand word embeddings. We humans, we understand English, right? We understand English, we understand Bahasa, we understand Mandarin, but computers don't understand any of this. What does it understand? Right? Zeros and ones, numbers, okay? Or what we call as vision language, okay? So I need to convert all words into numbers before I feed into it, okay? So when I convert into numbers, let's do it intuitively, okay? Let's say I assign a vector to a word, okay? How do I do it in human form? Maybe I ask a few questions about that word. Okay, for an example, it's a very arbitrary example that I put on the screen. Maybe for the word king, I ask a question, does he have authority? Then yes, yes, then I assign 1. Have a tail? No, 0. Rich? 1. Gender? Male? Okay, -1. Okay, so we assign numbers based on some attributes of that word. Okay, that's a very arbitrary. So all the other ones are self-explanatory. Now I want you to do a very simple calculation. Okay, to understand another aspect of this environment. Take king, you minus man, and then you add woman. What do you get? Take the of king, you minus man, and you add woman. What do you get? king minus man plus woman. What is the vector that you get? You get the vector of the queen. Okay? You get the vector of the queen. What does it tell you actually? I just randomly took a few words. We did like linear algebra, A minus B plus C, those kind of stuff. So we take the vector of king, we minus the vector of man, added the vector of woman, and then suddenly we are getting queen. What I'm trying to convey here is, when we do vector embedding, words that have similar meaning will be close to each other. Words that have different kinds of meaning will be away from each other. Okay, so that's how these vectors are assigned to words. Okay. So in our example for king, I gave 4 vectors, right? 4 numbers, right? What is the dimension of the vector that is being used in real world models? So I would like to ask you to Google up, check in Google, what is the dimension of word to vec model? Word to vec is the whole word model by Google. So anyone check and let me know. What is the dimension of the word embedding in word to vec? I think it's 300. What's the dimension of the word embedding of word to vec model? Word to vec would be 300 something. And can you quickly do for GPT-3, the first version of the ChatGPT model? You will get a very beautiful number. Not the parameters, the dimension of the word embedding. Is it GPT-3? Yes.
That's the largest dimension.
I'm not sure what you guys are. What is the output over there? Okay, let me give you the answer. 12,288. What does this number mean is, in GPT-3, in its vocabulary, it has a vector assigned for each word or each token, to be precise. The vector size is 12,288. Okay, so just now in the king, you saw 4 dimensions, right? In GPT-3, it's 12,288. All these features defining the words that you see on top, okay, or the token that you see on top. So this is where this transform architecture begins. You have to understand that all these words have a fixed vector whose size is 12,288. Okay. Now, naturally, you might ask the question. So, what does this? Just now for king, we asked the question, right? As authority or not, as tail or not. So that's a very simplistic understanding. So you might ask, what does this first number refer to? What does the second number refer to? Honestly, no one knows. Okay, because when these models are trained by OpenAI or Google, they do this neural network training, and then they use this algorithm called backpropagation, which you will learn when you learn deep learning. And based on that, the model optimized for these numbers. So that's why they say the cutoff rate of training. So maybe if they train today, these embeddings are based on data in the internet up to today. And these words get assigned these kinds of numbers to it for it to understand that this vector refers to this kind of words. Are we clear over here? Any doubts on this? Because you have to understand embedding metrics before we go into the subsequent parts. Okay? Now, once we understand embedding metrics, my next question is, what is the drawback with having a static embedding? When I say static embedding, you have a fixed vector to represent a word. What is the drawback with having a fixed vector to represent a word? Yes. Outdated. Outdated information is part of it, but there is another major drawback in having a fixed embedding to represent a word. Anyone would like to think of an example of that? If let's say I take a word cafeteria, so if I take a word and then I assign it a vector 1011, so that word is the fixed static embedding. If I use it for that word in all contexts, what is the drawback? Exactly. There is no semantic or contextual meaning to it. I will give you a very concrete example. You look at this three sentence, and you will see a word repeating in all the three sentences. Can you see what's the problem with having a fixed vector to represent that word in all the three contexts? So that word is right. In the first sentence, it refers to direction. In the second sentence, it refers to correctness of something, the correctness of the answer. And in the third sentence, it refers to kind of a legal or fundamental, it's like what belongs to you. It's a fundamental right. So if I go back to this embedding matrix, if I go and look for right, it will have a set of vector. If I use that vector in all these three contexts, then my model will start hallucinating because the meaning of right is not the same in all these three, it is different in all three sentences. So I cannot use the same vector to represent right in all three scenarios, right? Can you think of other examples where one word can mean two different things in different scenarios? What we call in English as homonyms. Sorry. C. But C is okay. That's one example. Another example could be model. So when you study computer science, machine learning model is a model, and then now just Met Gala happens. So fashion model is also a model. So, but the meaning is totally different, right? When I talk about apple, apple can be a fruit, or apple can be your tech gadget. So let me do it intuitively. As humans, how do we understand what does that word refer to? How do we derive the meaning of a word? How do we understand the context of the word as humans? What do we do?
Surrounding context.
We look at the preceding words, subsequent words. We look at the surrounding words to understand context. If you remember my first question, I asked why before 2017 we will not be able to do it. Those models, it looked one word at a time. It looked in sequence. It didn't look at the faraway words, the surrounding words to predict the next one. So this architecture is going to look at the words surrounding it. At the words surrounding it to understand the context. So what attention does. So if you remember the title of the paper, attention is all you need, right? So what attention is going to do is, it's going to take the static embedding, the initial direction of laptop, as a word, and then it's going to improvise the embedding of that word to incorporate the contextual meaning of that word. Okay. So the goal of attention block is to determine how much should I adjust the initial direction of that vector so that the contextual meaning is incorporated into it. So that's the goal of the attention block. Okay. I have an initial direction of the vector, let's say 111. How much should I adjust this initial vector so that we understand the context of that? We will go through a very simple example to understand it intuitively. Okay, so my example is going to start with this 8-word sentence. A sleek, powerful laptop at an affordable price. Let's assume you are putting this into your ChatGPT. Okay, let's assume you are putting this into your ChatGPT. And the first step that happens is, it takes in your query, it goes look at the embedding matrix. If you remember the embedding matrix that we had, So this embedding matrix, it goes look up what is the vector for all those 8 words. Okay, all those 8 words, it gets the vector for it and then it arranges like a matrix. Okay, and the size of a matrix is 12 to 88. If you remember, I said for GPT-3 the dimension is 12 to 88, right? So my example is based on GPT-3. So 12 to 88 by 8 columns, 1 column for each of the word. Are we clear here? Anyone not on the same page? Okay. And then you click enter, it goes into the attention block. Okay. Now we are going to look at things will be a bit complicated, but we will try to understand it intuitively. It might take around 10 to 12 minutes. Okay. So inside the attention block, you are going to see 3 keywords: query, key, and value. QKV. Okay. So let's take a very intuitive understanding of. We start with query. What does query means in English? Query, structured query language, SQL. What does query mean in simple English? What does query mean? I mean, in simple English, it's question. You're asking a question. Okay. So basically, over here, each word is going to ask a question about the surrounding word. So that's what's happening in query stage. So for an intuitive example, I'm asking, the word laptop is asking, hey, is there an adjective before me? Okay, because adjectives can add meaning to a word. Okay, so let's take an example of the word laptop asking, is there an adjective before me? So like I said, we humans ask questions through language, but these words are very picky. They cannot ask questions like that. They need to ask questions through numbers. So I need to produce a vector. How do I produce a vector? I need a matrix of weights to be multiplied with that vector to produce another vector. Okay? So that matrix on your left hand side, on the utmost left, it contains a matrix of 128 by 12 to 18. Okay. You might ask, how do they come up with these dimensions? So for that, I hope you remember the rule of matrix multiplication. The columns of your first matrix must match the rows of your second matrix. That's the rule for you to multiply matrix. So that's how they derive the dimensions of the matrix. I hope I don't have to go into matrix multiplication. Anyone needs help with that? No, right? Okay. So that matrix over there will be multiplied with the embedding of your words. If you remember these 8 embeddings of your words. So I just pick up one of the embedding of the 4th word, which is laptop. Okay. So you multiply with the matrix of your query. Then you will produce a new query vector for each of the words. And when I join them, you get a query matrix for your 8 words embedding, 8 words query. Anyone not able to follow with this? So meaning this query matrix is basically each of your words asking a question about the words around it. Is there an adjective before? Okay, that's query part. The second part of it is QK, key. So to understand key is basically those words answering that question. So when somebody asking if there is an adjective before me, so sleek and powerful will be answering, hey guys, I'm here. I'm the adjective over here. So again, how do we generate that answer vector? We will have a matrix, what we call as value weights. We multiply with the embedding of the original words, and then we will generate this value matrix. Basically, this matrix is each of the 8 words that you put in the query, answering if they are an adjective or not. So this is called key matrix. Query asking question, key answering those questions intuitively. Okay. Anyone lost me over here? in Q and K? Come on, right? I hope so. When I have a query matrix and I have a key matrix, if I do a dot product between these two matrices, which means each, let's look at the left grid, okay? So on the top row is all your query matrix. You have one vector for each of the words. And on your left-hand side is all your key matrix. One row for each of the words. When I do dot product between these two vectors, what do you understand if the dot product produces a big number, a big positive number? They are close to each other. If you remember my mathematical review, when two vectors are close to each other, they will produce a big positive number. So think about this intuitively. Laptop is asking, hey guys, are there any adjective before me? And then sleek and powerful answering, hey guys, yeah, we are the adjective before you. If you look at the grid, the intersection between laptop and sleek and powerful will have a large positive number. And if you also correspondingly look at the last word in the query, which is price, and the word affordable, we can see affordable will have a large positive number over there. Okay, so when the query and the keys are close to each other, you will produce a large positive number. And so that's the grid on the left. So what does the grid on the right means? So if you remember my second concept that I reviewed, softmax. So when you look at the columns, the numbers are very arbitrary. Some are very large, some is very small. If I want to transform them into a value between 0 and 1 and change them to a probability distribution, then I do a softmax for each column, which results in this very clean, standardized values. So when I look at, let's say, embedding number 4, which is my laptop, I can see that 42% comes from sleep, 58% comes from the embedding of powerful. Okay, so basically so you understand the concept, right? One is dot product, the other one is softmax. So let me remove one of the metrics. So let's come up with a clean one. So this matrix is what we call as attention pattern. What it tells us is, it helps the model deduce which words are relevant to which other words. So when you look at this attention pattern, you can see that the second and third word, which is sleek and powerful, is relevant to the word laptop. And the word affordable is relevant to the word price. So this is how the model learns which words are related or relevant to other words. Okay? So my next question is, why do you need to know which words are relevant to other words? What do you do after knowing, okay, these two words are relevant to this word? What do we do after that? Try to think with relation to the initial question that I had. So you cannot use a static embedding for all words, right? So you have a fixed embedding for a word. You cannot use that in all scenarios. Now you know the context, which words are relevant to the other word. What do you do to the fixed embedding? Adjust it. So we started with the word, a direction vector for laptop. Now we need to adjust the word laptop so that it has the meaning of sleek and powerful. So the next question, how much should I adjust? Right? You cannot arbitrarily just pull the vector somehow, right? You need to have a numerical quantity of how much you need to adjust, right? So that's where the third component of attention comes in, which is values. QKB, query, key. The third one is value. Before I explain what does value mean, let's look at the operation. There is no price for guessing what we have to do. It is deep learning. So you will take one matrix, multiply with the original embedding matrix. So that matrix of weight is what we call as value weights matrix. Multiply with the original embedding matrix, and we produce this value matrix for our query. Okay. So what does each of the column means? What does each of the vector means? It means if this word is relevant to the laptop word, then this is how much I should adjust the word laptop. Okay, so you can, and I have put the explanation of that. So if this word is relevant to adjusting the meaning of some other word, then how much should be added to the embedding of the some other word? So let's look at an example. So this word and this word is relevant to the word laptop. The second word and third word is relevant to our fourth word, right? So how much should I adjust the word laptop? Is I should add this embedding and I should add this embedding. So that's the meaning of value matrix. It tells you how much should be adjusted to the relevant words in the original embedding. Anyone lost me here? Okay, if that's the case, but we know from the attention pattern that the second word contributes 42%, and then the third word contributes 52%, 58%. Sorry, yeah, 42, 58%. So what we do is we take the value matrix. So on the left hand side is called your value matrix, value vectors. This one. So each of this vector goes to the side just now, and then we multiply it with the weightage that you deduce from the attention pattern. So it's like a weighted kind of multiplication. We don't take the whole of the value vector, but we weighted it 52%, 58%, 42%, and then we sum up the total of it. So if you see, sleek and powerful will have some weightage. All the other words wouldn't have any weightage. So up there is embedding number 4, which is laptop. And the words that are affected is sleek and powerful only. All the other words have 0. You multiply with 0 of the value vector. And when you sum up, is your delta E4, which means that is how much we will be adjusting laptop to embed the context of sleek and powerful. So I have put the equation over here. So this is the original embedding or the vector for laptop. And you add with the delta of it, and you get a new direction. The direction of laptop will be changed in a way that it understands that it is not a normal laptop, but a sleek and powerful laptop. Any questions? So to recap back, this is what happens in an attention head, a single head of attention. You have your original embedding. Let's say you put in a query in ChatGPT, it takes the original embedding from the embedding matrix, pass through query. So each of the word is going to ask question about the surrounding word. How do we get that? We have a set of metrics called query matrix. Multiply, you get query matrix. And then the key matrix is going to generate answer for that question. You have a set of metrics, multiply with the original embedding, we get value matrix. And then we do a dot product between key and query. We see which words are relevant to which word. So that's the attention pattern matrix. And then we generate value matrix. Value vectors basically tell you if that word is relevant to another word, how much should be adjusted. Again, a matrix multiplication will provide you value matrix. And then you multiply with the weights from the attention pattern, and that gives you the total amount of adjustment that has to be done to the original vector. And that's how you embed contextual meaning into the original vector so that it understands more words. Any questions before I move further? But if you understand language, adjective is not the only thing that can add meaning to a word, right? You can have adverbs, you can have verb. Sometimes it doesn't even have to be grammatical. Okay? You can say that the cat crossed the bridge and it catched the mouse. When we look at the sentence as humans, we understand that it refers to the cat and not the bridge. But how does the model understand? It looks at the overall context, right? When you look at the word Harry, what comes to your mind? Harry Potter or Prince Harry? Again, it depends on the context. What happens before that in the text? If I have been talking about Hogwarts, then you know it's Harry Potter. But if I talk about the palace, the royalty, then you know it's Prince Harry, right? So a lot of things can affect the context. So the transformer architecture doesn't depend on one single head of attention. It has multiple heads of attention. Okay. So in GPT-3, and I will give you the answer, there is 96 heads of attention happening parallelly. So when you click that query, press enter, the original embedding goes into 96 different heads. Like over here, you see 4 different heads. Like that, there are 96 different heads going through parallelly. So all these heads look at different aspects of that sentence. One looks at adjectives, one looks at verbs, one looks at verbs, different kinds of things. So you will have different matrices. One key, the QKV matrix, you will have different sets of QKV matrix for each of the head. And what happens at the end of it is, each of the head will produce how much the original embedding should be changed. And then what we do is we sum up all the delta and then we apply it to the original embedding. So the expectation is it would have absorbed a lot of context, and then the original embedding is adjusted to incorporate all those contextual embeddings, all the contextual changes. Clear? So GPT-3 has 96 heads. Doesn't mean that GPT-4, GPT-5 will have more heads. But the key is that operations happening parallelly. Not like the older models, it doesn't happen sequentially. It happens parallelly thanks to GPUs and TPUs. Okay. So this embedding goes through attention block, 96 heads. It comes out. You have an adjusted embedding for each of the words. So let's take our initial example, 8 words. Each one has its own vector adjusted already for the 96 context. Okay. What happens next? I mean, since you guys haven't gone through deep learning, these things might feel a bit abstract, but let me try to make it intuitive a bit. So what happens is, on your left-hand side, those adjusted embedding is going to go through neural network. Okay. You can call it multi-layer perceptron, or there is also it's also called feed-forward neural network, FFNN. Okay. Anyone already understand how does neural network work? Sort of, kind of. Okay, so I don't want to bore you to death with the details. Okay. You have the adjusted set of embeddings. The first the first vector that you're seeing is, it is going to be multiplied by a very large matrix. To be exact, 4 times larger matrix. Okay. Why do we want to do that? We have a marker pen. Is that marker pen? Take a break, guys. And if you have any questions, feel free to. Okay, so over here I've drawn a 2D plane. Okay, if I ask you to represent an information inside this 2D plane, there is only so much of the space for you to represent information. Okay, let's say I have 10 here, I have 10 here. So at max, you have like 100 places for you to represent information. What if you have 150 information, but you want to represent it into this thing? It'll be difficult, right? You might be superimposing 2 information on the same line. Okay, that's how you can fit 150 into 100 space. Okay, but let's say if I project it a bit and give you from this 2D space, I project it into a 3D space. Then you get another plane for you to play with that becomes 1,000 places, right? So you have more spaces to represent knowledge or more information. So basically, intuitively, what's happening over here is the original vector. Do you remember what's the dimension? Right? This was the original dimension. When I multiply with a bigger matrix, and in GPT-3, it's exactly 4 times of it, you will get something just less than 50,000. I'm not sure of this number, but you will see a 49,000 kind of dimension. So you are projecting from 12 to 88 dimension. You are expanding the dimension to slightly below 50,000. So similar like this example, from 2D when I went to 3D, you can represent a lot of information, right? So similarly, what the neural network doing is from 12 to 88, it's projecting to a very larger dimension so that more knowledge can be represented or embedded into that vector. I give you a very easy example to understand. Sometimes you might realize that ChatGPT or Gemini have facts stored in it. If I go and ask who is the 6th Prime Minister of Malaysia, it might be able to answer that Najib Razak is the 6th Prime Minister of Malaysia. You might be wondering, how does it understand this fact? It's a knowledge, it's a fact. How does it get stored? It's because of this neural network. It expands the space, it stores this kind of facts and knowledge, and then it undergoes this activation layer. ReLU is called rectified linear unit. I don't want to explain the mathematics behind it. It might be complicated. So it undergoes this transformation, and then you can see the size of this vector and this vector. It's smaller, right? So what happens is, at this stage, from 49,000 something, it's projected down back to this dimension. So you expand, you store knowledge, and then you squeeze back to the original dimension.
Is that a process in tensor?
Tensor. I'm not exactly sure on the technical term of it. I'll check and let you know. Okay, but intuitively, this is what's happening. You expand, you store more knowledge, and then you squeeze back to the original dimension. I'll check on the technical. So now you have a different set of adjustments that you want to do based on the context that you provide, based on the facts that it learned. So what do? You add this adjustment to the original embedding of that, and you adjust it further. Now it has some knowledge or facts to that particular embedding, to the original embedding. Okay? So if you remember, in the attention layer, we looked at surrounding words. We adjusted the meaning based on the context. And then in the MLP layer, we add more knowledge, more facts, and then we adjust the embedding based on the knowledge and facts. So we have much richer embedding for that particular word. And over here, it doesn't look at surrounding words. Each word is treated as it is. It doesn't look at the right word or left word or anything. The context and the knowledge and facts is embedded into those individual words. And again, it happens parallelly. So remember, when you type in GPT 100 sequence words, all those 100 words of process parallelly. So that's where you need GPUs. CPUs cannot handle those kind of heavy processing. And at the output of it, you get the adjusted embedding, new embedding, adjusted embeddings for each of them. Okay? So that's one transformer block, one attention block, and then one MLP block. And it doesn't happen once. You can see that this transformer block, the attention MLP, repeats so many times in that transformer architecture. In GPT-3, it repeats 96 times. And that's the process that's happening before your ChatGPT or Gemini provides you the output of the first one. So this attention MLP happens so many times before it comes to this stage. And each time it doesn't look at the same context. So the first 96 attention blocks, it looks at 96 different things. And then after the MLP, when it comes to attention again, it looks at a different set of 96 things. So you can see the magnitude of scaling that happens. Okay, this is GPT-3. Now we already have GPT-5. GPT-5 has trillions of parameters. This was just 175 billion parameters. So at the end of it, at the end of this layers, what we'll have is this matrix down here. Okay, the earlier embedding of that word is adjusted over so many repetitions, and we come to this. But this is not what we want. What we want is, what's the next word, right? We want to predict the next word. So what happens in predicting? The model doesn't look at all the other words. It only looks at the last word, which is, in our case, what's the last word? Price, right? A sleek, powerful laptop at an affordable price. It only looks at the word price. Do you think it's wise to only look at the last word and then predict the next word in our case? If I look only at price and then I want to predict the next word, would it work? But in our case, you have to remember that this embedding, the original embedding, has gone through so many layers of attention MLP, that it is expected that the embedding for price has incorporated that, hey, I am the price of a sleek, powerful laptop, and I have to be affordable. Because you have gone through so many attention, and you have gone through embedding the MLPs where the facts, the surrounding context has been embedded. So that's why at the last stage, it only looks at the last, the embedding of the last word. And again, no price for guessing. It is going to multiply with a large matrix, okay, which we call as an embedding matrix. So what do you think is the dimension of W and embedding? Let's look at the dimension of the last vector. What is the dimension of the vector? The vector of the last word? Yes. 12288 times 1, right? Now I need to multiply this with a matrix up here so that I can get, what do I want is, I want a probability for all the words in the dictionary of the model. So in GPT-3, when you had the embedding matrix, it had somehow around 50,000 words in it. Okay, so my matrix should be of those 50,000 words times 1288. So that when I multiply this matrix, I will have the output matrix will be somewhere 50,000 times 1. So this is the 50,000 times 1 vector. Okay, it's not exactly 50,000, it's some 50,000 something words in GPT-3. So GPT-4, GPT-5 might have more words, more tokens into it. So I'm just showing this to show you the scale of that WU matrix. The dimension has to be same as the dictionary, the vocabulary, the size of your vocabulary. So what we have here is a number for each of the words in your vocabulary. Arbitrary number scaling from negative infinity to positive infinity. Difficult to understand. What I want is, what is the most likely next word? Which word has higher percentage of coming as the next word? What do I do? Remember the concept that we talked just now? How do we convert arbitrary vector of number into a probability distribution? Softmax. Softmax. So you do softmax, and then you convert those arbitrary numbers into a probability distribution. And the word with higher percentage would be predicted as your next possible word. That's how your ChatGPT streams word by word. So it predicts the next word, and then with the next word, it passes through again the transformer, and then it predicts the following word. And you can see it happens at a very fast scale because of the processing power that is available currently to this infrastructure that we have. Was it ready? Sure, it was a read. If it is the first time, because even I had to go through 4 to 5 times to really understand. But I hope I give you the intuition of it, so that when you go back and study, especially the video that I use for this is the 3 Blue 1 Brown channels videos. They have very intuitive and informational video that can help you to understand things intuitively. Okay. I haven't answered one question. Why is the output of ChatGPT non-deterministic? Why, when you put the same query in 2 different chats, the output goes totally different?
Let's do action.
But the calculation is going to be the same, right? All the matrix multiplication, the embedding, and everything is going to be the same.
With just one number is just changed everything.
It's the main trick happening over here. So now when I do a probability distribution, you can see this word has 78% of being chosen, and this word has a 16% of getting chosen. What if in a different probability distribution, 2 words have almost 50% of getting chosen? So when the probability is almost similar, then when I do a random sampling, maybe the first time I get the first word, maybe the second time the sampling gets the second word. And then when I feedback the different second word into the whole transform architecture, the whole thing will change. So that's how the output is non-deterministic, because it's based on probability. When it comes to probability, there is chances involved. Maybe you can get this, or maybe you can get that. Okay, just because it's 16%, it means there is 16% of this word becoming the next word. So when I do a random sampling, maybe if you do the same query 100 times, 16 times, this might be the next one. 78%, that might be the next one. So that's why you get a different output every single time. So that answers the question, why is the output non-deterministic? And that also answers why is it streaming one by one? Because it predicts one word at a time, and then it feeds with the predicted word into the transformer architecture again to predict the next word. So that's why in your ChatGPT, what always comes word by word, one word at a time. Any questions you guys would ask? We can go into a okay, I will share this, or maybe I'll share this link in the chat. Okay, so this is a site that I found online. I was going through YouTube videos to understand this. So basically, the link is in your chat, the Teams chat. Basically, just visualizes what we went through just now. It's a smaller model, not GPT-3, but the concept is still the same. When you look at your left-hand side, so this is the query that is being fed. Data visualization empowers users to. Okay. So now we need to predict the next word, which it predicts and visualize. So if you look at the visualization here, we start with embedding. So it assigns a vector for each of the word. We start with the initial token embedding. And then this part I didn't cover in my slides, but on top of encoding the meaning of the word, it also encodes the position of the word. Okay, because when we understand sentences, we understand sentence with relation to its position in the sentence also. Okay, we understand the meaning of the words with relation to its position. So it encodes the meaning and also the position. And then you can see in the first transformer block. So a transformer block is basically a combination of attention and one MLP. One attention and one MLP is transformer block. So in one transformer block, you can see the QKV going in. So first the query matrix, and then the key matrix and the query matrix. They do a dot product, and this block is your attention pattern. Okay, is your attention pattern after you do the dot product between Q and A, and then you do a softmax to constrict the values between 0 and 1. Okay, and then you multiply with the value, and then you adjust the embeddings, and then it goes into your MLP, multi-layer perceptron, and then you embed the knowledge and facts, and then it comes over here. So if you see in one transformer block, you have 12 heads. Okay, so this is the part where I say GPT-3 has 96 heads, right? So this model has 12 heads, and it has 12 transformer blocks. So which means the attention and MLP repeats 12 times. And then at the end of the day, after the 12 blocks of transformers, you do an embedding over here, and then you assign a probability for each of the one. So over here, visualize has the higher percentage. So in the random sampling, it predicts visualize. So if I click generate again, it passes through the whole embedding to visualize, and then it predicts the. So over here, if you see, N has a higher probability. But again, because of the random sampling, it predicts the as the next one. Okay. If you look at the temperature here, you might have heard about it. When you build AI application, they might tell you that if you don't want the output to have a lot of variation, reduce the temperature. If you want it to be more creative, increase the temperature. So we can see a demo here. If I put the temperature as 10, you can see the third word getting chosen. You can see a lot of lower probability words getting chosen. But if I reduce the temperature to 0, you will see almost the top one going off. What's really happening in the temperature is, again, I don't want to go into the mathematics of it, but if I go back to my deck, I will just let you know where does temperature play a part. So basically, temperature plays a part in this softmax function. So right now we take an exponential of x1, right? The temperature, if you set it up, it will be exponential of that value divided by temperature. So when it is big, then you will have a variation of probability. When it is small, then you have constructed probability. So this is where the temperature comes in the softmax application. So let's not go into the mathematics of it. Okay. So I've shared this link in your Teams. You can go back and try to play basically a visualization of the concept that I explained just now. From your original embedding, how does it go into attention? How does it go into multi-layer perceptron? And how does it come up as the next one prediction? Do we still have time? All right. Do you guys want to do a hands-on of how to use transformer model? All of you have, I mean, some of you don't have laptop, that's why I'm asking. How do we go with it? Okay, let's do a simple one. Try to open your Google Colab, those who have laptops. So basically, this demo is, I found this demo in the YouTube video that I provided the link on top there. Anyone have used Hugging Face over here? Okay. Anyone else? Have you used Hugging Face? Okay, that's good. So I can introduce you guys to it. Let me open it up. So Hugging Face is like GitHub for AI models, transformer models, or other AI models. So this is open source. So when people, the open source from like DeepSeek, Llama models, they publish it to Hugging Face. So if you want to use them, you can pull it from, it's like a GitHub. So you can pull it from here and you can build applications with it. Okay, that's the first use of it. And then since it's open source, do you remember when I was explaining about the attention pattern? I told you there is a query matrix, key matrix, value matrix. So those metrics, the weights of those metrics, you cannot get it for your open AI models or Gemini models because those are proprietary. Those belongs to OpenAI or Google. But this open source models, you can get the weights and biases because they are published for public. So you can use those weights and models and you can fine tune for your own use cases. So I will not go into the fine tune part, but let's look at the inferencing ones now. Okay, so those who are following through, create an account in Hugging Face, or if you already have an account, just you can log in first because we will need the access token from Hugging Face. May I know how many of you are following through? Okay, just making sure people are. Let me just log in and then. Okay, so once you log in, you will see this page here, Hugging Face. Okay, now let's go back to our Colab. Okay. Let's do the first thing first. On the side here, on the left tab here, you will see secrets. So this is where we will have to save the access token from Hugging Face. So you can go to your Hugging Face. See the icon on the right here. And you click, you'll see access token. Okay. So I think for you guys, since you have not created a token, you can click create new token, change to read, and you can name anything. Just give some arbitrary names. Just put APU demo. You can create the token, and then you copy it. You come back to your Google Colab, click add new secret. Then you name this HF token, Hugging Face token. Then you paste the value over there. And then click notebook access. So this is basically just housekeeping so that it can connect with your Hugging Face account. Make sure the notebook access is ticked. Okay. Okay, so let's move to this first part, which is called inference. So basically, inference means you use the model to generate text. That's the interpretation of inference. So when we go to Hugging Face, right? Okay, when you go to Hugging Face, you can click on this part here and then task. You can see there are a lot of models open source models that are available over here. Multimodal, natural language processing, for computer vision, audio. So all those are open source models that has been publicly published for you guys to use. And Hugging Face also made it easier for us to pull through our codes. When if you look at the code over there, it has given us this from transformers import pipeline. Okay, so this pipeline is basically going to structure the pre-processing, the inferencing, and the output part. So run the first step first. So let's do the pip install transformers. So transformer is the module that is going to pull the models from Hugging Face. Oh yeah, I forgot something. Before you run it, go to runtime, click change runtime, and make sure it is the default GPU. By default, it will be a CPU in your Colab. Change it to GPU because, like I said, everything has this models run is very computational heavy, so you need a GPU for you to run. Change to default GPU, and then you click save, and then you do pip install transformer. Anyone still stuck somewhere? Are you able to run? Guys, have you completed this step? Stop. Okay. Then you go to the next block here. So it's from transformers import pipeline. So pipeline is the one going to structure the pre-processing, modeling, not inferencing and model. Okay. Then you can see here I've written model name. Then there is DeepSeek's one. So when you go here, when you look at the task, let's go to text generation. So you can see text generation has like 367,000 models, right? It is a bit slow. Okay. So it explains about text generation. Then you can check the models that are available for text generation. And when I look for DeepSeek, these are all the models that are available under DeepSeek. Okay. So we picked one of it and then we provided it in the Colab here. You can see here that I picked one with 1.5 billion parameters. So the bigger the parameters that you have, so you can filter for parameters over here. So the bigger the parameters, the longer the model is going to run because there are more metrics for it to multiply, more layers for it to go through. Okay. So how do you pick a model's name? So if you want to pick, let's say this model, just click into it, and then you can see the model's name on top. So you just copy this model's name, and then you can go and paste it over here. Okay. For this model, in the demo purpose, I've picked the 1.5 Quen DeepSeek model. And then the task is also an input from your side. So basically, it's the task that we saw just now. If you go to task, so these are the tasks. You just key it in small letter. So for text generation, you just key it in as text generation with the dash in between. Okay, and you have so many tasks. So based on the model that you've chosen, you just key in your task. And then you create an instant of the pipeline. And then the generator, you also give the prompt of what you want to try. For now, I explain how transformer architecture works in simple terms. Prompt maximum length is 100, so meaning that it needs to generate 100 tokens. Truncation is true, which means after the 100 token is generated, it will stop generating output. And the number of written sequences is how many outputs I want to generate. So when I key in 2, it means it will generate 2 responses. We will look at both responses later. Right now, I've commented the second response. You can see that I took the first response from results and then tried to print it out. Let's print out the first response first, look at the first response, and then we will print both response. So you can run the second block. Make sure you have choose the compute type to GPU. It will take quite a little bit extra time for the first run, and then the second run would be much faster. While it's running, if you have any questions, feel free to let me know. And you can see here, it's loading the model. So it's pulling the model from Hugging Face, loading it to your Colab, and then it will pull the weights and biases, and then it will do the calculation. While it's running, let me just explain what's in the fine-tuning part. So basically, these models are trained on all the text in the internet. Let's say you have a very specific use case. Let's say you want to build something for health industry or something specific for construction industry. You might want to fine-tune the weights of the model based on your set of data. So that's where fine-tuning comes in. So you pull the weights and biases, the parameters from the open source models, and then you retrain back using your own data. So we will not go through the fine-tuning part. You can check the YouTube video link that I put on top of the Colab. Over there, he has explained how do you do the fine-tuning part over there. Okay. Okay, I think our model, our generation is going to end. Anyone already got the output? Nice. Yep. Okay. So over here, you see in the generated text, this is our prompt. Explain how transformer architecture works in simple terms, right? And then this is what it has generated. Transformer architecture is the type of neural network. Basically, everything that we have gone through today, it generated as a text. And then you can see overall transformers are, and then it stopped over there. Mainly because we said truncation through. So after the 100th token, it stops generating. Now, what we will do is you try to uncomment this part, uncomment the text to, and uncomment the second print command, and then rerun it back. So since we put number of written sequences is true, it will generate two responses, and we will look at both responses. You just uncomment those two lines and then rerun it back. So when you have free time, you can explore Hugging Face to see what other models are available. You can try out with higher parameter, the more 500 billion, even to up to 500 billion parameter models. But just keep in mind that it will take a lot of time. Okay, now we have generated two texts. Okay, so the first one is in this part, generated text. This is the first one. And then the second part is over here, the second generated text. Do you see that the first output and the second output is totally different? It started off the same, it started off in same manner. Transformer architecture is a type of, but after the type of, both the output deviated. The first one goes, it's a type of machine learning model. And then the second output goes, is the type of neural network for processing sequential data, right? So that's because of the probability sampling that we saw in the end of the architecture, transformer architecture. Right? Any questions on this? So you can go back and try out. The YouTube video link is up here. So this is the YouTube video that I got this demo from. Just click the first part of it. You can follow this YouTube video to do the fine tuning on your own. Okay. You can pick up any model. You can train it using your own data. So if I just show you a little bit on the fine tuning part, you can see here, this demo is providing its own data. It's a very small data, but if you want to train a transformer model, you need to use a big chunk of data. But for demo purpose, they used a very small data, retrain the model, and then try to publish it. So in Hugging Face, when you retrain a model, you can publish it to Hugging Face as your own model. So that other people in some other places, they can use those fine-tuning models for their use cases. So it's sort of a GitHub for you. I'm actually done with my sharing. Any questions? There's no question, we can close the session. Hopefully it was useful for you guys, even though it's too much to hold at the same time. But when you do a review back home, mainly go through the 3 blue 1 brown videos, which will be helpful for you to grasp the concept of it.